Welcome to Fluid Mechanics N6. Today's video is going to be on ventilation. This is a module that is quick and easy to understand. Should you get a question from this module in your exam, by the end of this video, you will be perfectly able to actually do that question. So please listen carefully because these are not the kinds of questions that a student should fail. They are quite easy when they have been nicely explained and the student has taken the time to work and understand. The first thing I am going to speak about is the classification of mechanical ventilation. In the first picture that you see, you have a ventilation system that has got a fan here on the inlet side of the ventilation system. And in the second picture here, it's again a ventilation system, but this time the fan is on the outlet side of the ventilation system. As you can see in the first picture, we are looking at a picture indoor, okay, and the second picture is a picture outdoor, okay. So when you have a fan on the inlet side, okay, of the ventilation system, then you're looking at a situation like that. When you have a fan on the outlet side of a ventilation system, you're looking at a situation like this, okay. It's generally outdoor when the fan is outside of the ventilation system or on the discharge side, and the fan will be indoors when it is on the inlet side of the ventilation system. You have definitely seen ventilation systems in your life. Probably in some buildings you walked in, you saw pipes on the roof, or maybe you might have seen some sort of equipment that was hanging on the wall, and with a fan that was there. That was just a ventilation system that you were looking at, okay. And so depending on the location of the fan, we can classify ventilation systems into three categories, okay. The first one is what we call the plenum system, okay. The plenum system is a ventilation system where the fan is on the air inlet side only, okay. So a system like this one that's got the fan on the inlet side only, that will be a plenum system. The second system is an exhaust system. Now, that one is when the fan is on the discharge side only. So what you're looking at in this second picture here, that will be an exhaust ventilation system. But you also have something that we refer to as a balanced system. And in this case, you have fans on both sides. So there is a fan on the inlet side of the ventilation system, and then you also have a fan on the discharge side of the ventilation system, okay. And so these are the three main classifications, if we may refer to them as mechanical classifications of ventilation, okay. These are the three that are very important, that may be worth remembering, okay, at least for you who is doing fluid mechanics N6. And so the type of ventilations that use fans can be divided into two categories, okay. You have ventilation systems that will have axial flow fans, and then you will have ventilation systems that use centrifugal fans, okay. And so we will talk a little bit about axial flow fans and a little bit about centrifugal fans before we move into looking at equations. And so an axial flow fan is most likely what you have seen when you looked at the ventilation system. They are the most popular, and so you will have a fan that is mounted like that on a shaft, and that fan is rotating. So basically the way an axial flow fan works is that it will draw in air, but the flow of the air will be parallel to the shaft, okay? And it will go in and be also propelled outward in a parallel direction to the shaft, okay. And so some of the advantages of axial flow fans is that, first of all, they are suitable for both small and massive applications. Okay, they are the most common fans that you will find. They are energy efficient, and because it is a simple design, you can also expect them to be cheaper than the centrifugal fans. Okay, so when you have a ventilation system that is using an axial flow fan, that ventilation system will be cheaper than than one that uses a centrifugal fan, okay, for the same capacity. Okay, and if I may speak of a disadvantage, okay, I will say that axial flow fans are noisy. Okay, this is one drawback with using them, and so if you need to look for a ventilation system for an application where quietness is a priority, then maybe looking into axial flow fans might not be a good idea. Okay, and so let us look quickly at centrifugal fans. And so the picture that you see here is a centrifugal fan. And as you can see, just by comparing the two pictures, you can see that the centrifugal fan design is much more complex than the axial flow fan design. And for that reason, you can expect a ventilation system that uses a centrifugal fan to be expensive. Okay, and the way it works is that the centrifugal fan will expel the air in a direction that is 90 degrees with the intake direction. So if the air is coming in horizontally, it may be expelled in a direction that is perpendicular to that horizontal line that the air came in with. Okay, I hope that makes sense. And this is accomplished through the centrifugal force that is generated by the rotating impellers. Okay, so that's basically what causes the air to be expelled in that 90 degrees direction. Okay, 90 degrees to the inlet direction line. Okay, so talking of some of the advantages, okay, when you have a centrifugal fan design for a ventilation, then of course it will be possible to operate with high pressure airflow, because a centrifugal fan ventilation system produces high pressure airflow. And so in applications where you need high pressure, that might actually be suitable for a centrifugal fan ventilation system. Okay, and also the structure is robust. I think even from the picture you can see that there is more robustness here than you have here. And one big advantage of a centrifugal fan ventilation system is that they can be quite quiet. Okay, so if you're looking into an application where quietness is a priority and you want things to be calm, then using a centrifugal fan ventilation system might be a good idea. But of course, if you have the means to afford it. Okay, so as a disadvantage, because the complex is design, the design is complex, sorry, then of course you can expect it to be expensive. Okay, so that's a disadvantage. It's got a complex design, and therefore that makes it expensive. All right, so this is just a little bit of theory on ventilation systems. And of course, I was just skimming the surface, not telling you more than you need to know to be able to answer a question on this particular module. So now we will jump straight into equations. And the most important equation when we're speaking of ventilation is Atkinson's equation. And Atkinson's equation is written like that. P is equal to K multiplied by S multiplied by V squared and divided by A, okay? And of course, you have another version of this equation that is like this, okay? So this is the other version of the equation that you have here. Okay, very, very important. And so what is what in this equation? So P that you have here is actually the frictional resistance, but it's just a pressure, okay? It's the frictional resistance. We refer to it as the frictional resistance, but it's just a pressure, okay? That's the pressure that you need to overcome the friction, basically. So that's why it is referred to as the frictional resistance, but it's just a pressure, okay? It is just a pressure. K that you see is the friction factor, okay? And sometimes in the question they may say to you, take Atkinson's factor to be this number, and they will give you the number. And so that will just be K, okay? S is the rubbing surface, okay? Or if you want, you can think of it as the weighted area. A is the cross-sectional area, okay? V is the velocity, and of course, Q is the flow rate. Now, when it comes to Atkinson's equation, you have to decide which format of the equation you're going to use. You can use the first format of the equation here, where it's KSV squared over A, or you can use the second format of the equation, where P is equal to KSQ squared over A cubed. Okay, these two are equal. Okay, we just played with the fact that velocity is equal to Q over A. So we replaced V by Q over A. And then when you do that and you work on this equation by replacing V by Q over A, what you end up with is this format of the equation. But this and this are the same. The reason I am giving you the two formats of the equation is so that you may choose which one is more convenient to use depending on the question that you get. If you get a question where they give you the velocity, then the first format of the equation here will be the best to use. But if you get a question where they gave you the flow rate, then the second format of the equation will be the one that is best to use, okay? It's gonna be quicker to get your answers by using this equation here if you have the flow rate. And if you have the velocity, use this format of the equation. But the two are the same, okay? And so, having said that, I just wanna speak a little bit about the cross-sectional area and also the rubbing surface or the wetted area, okay? That needs to be explained because when it comes to questions on this particular module, many students fail because they do not know the difference between S and A, or sometimes they may know the difference, but they just don't understand how to get S particularly, okay? A is quite easy to get because it's a cross-sectional area, but when it comes to S, sometimes people get confused. And so I just wanna show it to you and explain it very easily so that you never forget and never struggle with it again. Okay, so now look at the picture that you have here. Okay, so of course what we have here is a pipe and we have water that is flowing through the pipe. Okay, of course, when we deal with ventilation, it is not water, but rather air. But for the purpose of explaining, I decided to use this example where we're dealing with water, because that may make it a little bit easier for you to understand, okay? So if we look at this pipe here, and let's say maybe its length is L, okay? So this segment of the pipe that we have in the picture, its length is L, and we have water that is flowing through the pipe, okay? And so now, what do we call the cross-section area? Of course, imagine if you were to cut through the pipe and look at what you have. What you will see is pretty much a circle, okay? And let's say that the diameter of the circle is d, okay? Then the cross-sectional area will be simply pi by 4 multiplied by d squared, okay? You're doing N6, by now you should know how to get the cross-section area of any shape that is given to you, okay? So in this case, because the pipe is circular, the cross-sectional area will be pi by 4 multiplied by d squared, okay? And as I said, calculating the cross-sectional area, that is not difficult, but where students tend to make a mistake is when they have to find the rubbing surface, okay? When they have to calculate the weighted area, that is where they make mistakes. And so I will explain it to you now. So basically, the wetted area is the area that is in contact with the fluid that is flowing through the pipe, okay? So you can see here, that's why I wanted to use water as an example, because water can make it easy to understand the term wet, okay? The wetted area, okay? So when you have water flowing through a pipe, if you want to see the area that is wet with the water, how will you get that? It's actually a lot simpler than it may sound. Basically, imagine that we cut the pipe, okay, and we open it up, okay? So this length of pipe that we have here, imagine that I took a knife and I cut it on top there, and then I opened it, okay? Then if you can picture this, you will see that what you will get is actually a rectangular shape, okay? Imagine having this pipe here, and then you take a knife or a razor and you cut it on top here so that you can open the pipe, okay? You can open it and make it flat on the ground. You will see that the shape that you will get will be a rectangle, okay? And the length of the rectangle will just be the length of the pipe. L, okay, that will be the length of the rectangle. But now this side of the rectangle is going to be equal to the circumference of the circle that you have there. And we know that the circumference of a circle is pi multiplied by d, okay? Because if I were to cut it on top here and pull it until it is a straight line, the length I will get will be pi multiplied by d. And so the area that is wet with water is all of this, okay? It's all the inside area of the pipe, all of this. And because this is a rectangle, therefore that area is the area of the rectangle. So what is it equal to? It's basically equal to the perimeter of the circle multiplied by the length. And this is what we refer to as the rubbing surface or the wetted area. It's the perimeter, okay, of the shape that you have in your cross section. In this case, it's a circle. So the perimeter of a circle, and then multiplied by the length of the pipe, okay? So that's what will give you the rubbing surface or the wetted area. And I have to say at this point that in a ventilation system, the type of pipe that you have through which air is flowing may not necessarily be cylindrical. In other words, the cross section may not be a circle. It could be a rectangle, it could be a square. But the procedure to getting the cross-section area and also the rubbing surface or wetted area is similar to what I just explained here, okay? Very, very important. And lastly, before we move on to examples, I want to speak of the air power. Okay, so the air power is given simply by rho multiplied by g multiplied by q and multiplied by h. Rho is the density, g is the acceleration of gravity, q is the flow rate, and h in this equation, when we're dealing with ventilation system, is the water gauge, okay? So that's how we will refer to it, okay? H is the water gauge. Very, very important. So that's how you will get the air power if ever you had a question like that. So let us look at our first example. A fan extracts 9.2 cubic meters per second through a cross-sectional square duct, which is 50 meters long, okay? So as you can see, the duct that you have here has a square cross section, as the question says, and the length of the duct is given to you as 50 meters. So L is 50. A pressure of 200 pascals is required to overcome the friction of the duct. Okay, so the pressure to overcome the friction, okay, is 200 pascals. Okay, that is what we refer to as frictional resistance, P. Okay, it's the pressure to overcome the friction. It's 200 pascals in this question. That they said use K in Atkinson's formula as 0.003, okay, 0,003. That's the value for K. And then they say calculate the cross-sectional dimensions of the ducting. Okay, so the cross-sectional dimensions, since this cross-section is a square, so each side is, every side is the same, okay? Each side is equal, okay? So it's B here, B here, B here, B here, because it's a square. So basically the question is asking us to find the dimensions of the cross section, but because it's a square, we're just looking for B, because each side has the same length, okay? Same dimension. So we're trying to find the value of B under these conditions. So first, let us look at the equation that we will use. As you can see, this is Atkinson's equation, but this one is the format where you have a flow rate. And we left out the other presentation of the same equation where you have velocity. The reason for that is because when you read this question, what you are given, 9.2 cubic meters per second, is a flow rate, okay? So it will be more beneficial for us to use the format of the equation where we have an expression for the flow rate, okay? It will make calculations easier and you will get to the answer a lot quicker than if you used the format where you have a velocity, okay? So that is what we have. That is the equation that we are going to use in order to solve this problem. And so given to us is P is already given, it's 200 pascals, K is 0.003, okay, and then Q is also given as 9.2 cubic meters per second. And then now we need to find A and we need to find S. Remember what I just explained. A is the cross section and S is the weighted area or the rubbing surface. Now the cross section of this duct, as you can see, is a square. So if we have to find the cross sectional area of the duct, it's just going to be the area of a square. Okay, and so A is equal to B squared, because that is how you will find the area of this particular square here, okay? So A is simply equal to B squared. And now we need to find the rubbing surface or the weighted area. Now to find the weighted area, you need to imagine that you have a fluid that is flowing through this duct, and the area that is going to be completely in contact with the fluid inside of the duct, what will that area be equal to? And as I said in the previous slide, the rubbing surface is equal to the perimeter of the cross section, okay, multiplied by the length, okay. So if we do that, then what is the perimeter of a square? The cross section is a square. What is the perimeter of a square? It's going to be B plus B plus B plus B. That's the perimeter of a square. So it's 4B. And then that multiplied by the length will give us the weighted area or the rubbing surface. And so you will have 4B multiplied by L. And in this case, L is 50. It is given in the question. L is 50 meters. And so it's going to be 4B multiplied by 50. So it's 200B. So we have A, which is equal to B squared. We have S, which is equal to 200B. And so as you can see, we have all the things that we need to be able to plug in values in this equation, and the only thing that will remain as an unknown is b, and so we can then solve for b to find the dimension of the ducting. Okay, so this is the equation that we using. Okay, again I will repeat, we use the format where you have a flow rate expression, because in this question we are given a flow rate. If we were given a velocity, we would have used the format of the equation where you have a velocity. Okay, it's just better to do it that way because it makes calculations easier and you get to your answer quicker. Okay, so plugging in values for everything, so what you get, p is 200, okay, k is 0.003. We found an expression for s in terms of b, so it's 200p, and multiplied by q squared. Okay, q is 9.2, so we 9.2 squared, and that's divided by the area cubed. Okay, now the area is b squared, so if you take b squared and you cube that, then you will get b to the 6. Okay, and so that is the expression that we will have. And as you can see, the only thing that we do not know in this expression is b. So you can solve this equality for b, okay, and find what the value of b is. And so that is what I did, and you will end up with b equal to 0.76 meters, or if you want, 760 millimeters. Okay, and if you can do that, that's pretty much it with this question. And this question was taken from a past paper, and so this is to give you an idea of how simple the questions on this particular module can be. Okay, and so it's so sad if you can't even grab these 5 marks. Okay, so please just make sure that you understand everything I explained in this video. That will guarantee you about 5 marks in your exam. The second example that we're going to look at is this one. Now, a question like this, of course, if you should get that in your exam, this here will be maybe 8 marks, okay? So you're looking at about 5 to 10 marks whenever you get a question from this module. Sometimes they can make it too simple, where you just have to apply one formula, then they will make that question maybe 3 marks. But I've not yet seen a past paper where there was a question from this module that was over 10 marks, okay? Because the questions are quite simple and easy to tackle. And that is why you wanna take this video seriously, because that will guarantee you somewhere between 5 and 10 marks in your exam. Okay, so let us look at this example. A fan delivers 25 cubic meters per second of air into a duct that splits into 2 branches, okay? So you have air being delivered into a duct that then splits into 2 branches. Now, the one branch is 110 meters long and 1.4 meters in diameter. And the other branch is 72 meters long and 1.1 meter in diameter. And then they say assume equal values for k. So k for the one branch is equal to k from the other branch. And also you are told that both branches discharge into areas at the same pressure. So P for the first branch is also equal to P for the second branch, okay? So now calculate the quantity passing through each branch. In other words, they want you to find the flow rate through each of the branches, okay? Flow rate through the first branch and flow rate through the second branch. That's what they want you to find. Okay, so let us go ahead and do this question. Okay, so it's question 4. The first thing is to pick which kind of equation you're going to use, which format of Atkinson's equation you're going to use. And of course, because again, in this question, we are given a flow rate, it's gonna be beneficial for us to use the format of the equation where we have an expression of the flow rate. Okay, so since the flow rate here is 25 cubic meters per second, you can see we have a flow rate given. So the format of the equation with an expression for the flow rate is the one that we will use. Okay, as I said earlier, it will make your calculations easier and you will arrive at the answer a lot quicker. Now, for the first, let's label these two branches, because of course this air is delivered into a duct that splits into two branches. So I will call the first branch 1, okay? The first branch, the one that is 110 meters long and that has got a diameter of 1.4 meters, I will call this duct 1, okay? And then the other duct, I will call it 2, okay? The one that is 72 meters long and that has got a diameter of 1.1 meters, okay? So now using Atkinson's equation, applying it to the first branch or the first duct if you want, okay? Then we can write it like this: P1 will be equal to K1 S1 Q1 squared divided by A1 cubed, okay? So this is just to say the pressure in the first branch will be equal to this K for the first branch multiplied by the weighted area of the first branch multiplied by the flow rate in the first branch divided by the cross-sectional area of the first branch. And then we have a similar expression for the second branch, okay? P2 will be equal to K2 S2 Q2 squared divided by A2 cubed, okay? And now that we have these two expressions, we need to take into account what we have been told to assume, okay? You are told that you need to assume, first of all, that K is the same, okay? The value for K for the first branch and the second branch is the same. So K1 is equal to K2. And also you are told that the pressure is the same. So P1 is equal to P2. So we have to take these into account. P1 is equal to P2 and K1 is equal to K2. Now, what is very important to see here is that if P1 is equal to P2, you can make this here equal to that, okay? You can make this equal to that. If P1 is equal to P2, then this here must be equal to that. And because K1 is also equal to K2, so you can even simplify these and take them out, okay? So what you will remain with is this, okay? An expression like this, where you have S1 Q1 squared divided by A1 cubed will be equal to S2 Q2 squared divided by A2 cubed, okay? And so remember, we are told that we need to find the flow rate in each of the branches, okay? Okay, so we're trying to find Q1 and Q2, but before we can do that, let us first find A1, S1, A2, S2. Okay, so A1 is easy to find. It's the cross section of the first branch. Remember, I told you that the first branch is the one that is 110 meters long and that has got a diameter of 1.4 meters. Okay, so finding the cross section, since we have the diameter, it's easy to find the cross section of the branch. We will just apply the equation for the cross section of a so a duct that has got a circular cross section. Okay, basically I'm trying to say we will find the area of a circle. That's all I'm trying to say, because this duct has a circular cross section. Okay, so doing that, then you will easily apply the equation pi by 4 multiplied by d1 squared. D1 is 1.4, so 1.4 squared here. You use your calculator and you will find that the cross section of the first branch is 1.539 square meters, okay? And then we can now find S1, okay? S1 is equal to the perimeter of the cross section, which is just the perimeter of a circle, multiplied by the length of the branch, okay? So we did already find an expression for that in my explanations in the example that I used there of the pipe that had water flowing. We found the expression for the wetted area when you have a pipe, okay? And so that was just pi multiplied by the diameter multiplied by the length. So for S1, it's going to be pi D1 multiplied by L1, okay? And D1 is 1.4, L1 is 110, so you use your calculator and you will find that the rubbing surface is 483.805 square meters. That is for the first branch, okay? And then we do the same thing for the second branch. We find first its cross-sectional area, okay, and the diameter D2 is 1.1, okay. Remember I said the second branch is my 2, so its diameter is D2, so 1.1 is D2. And using your calculator, you find that the cross-section area of the second branch is 0.95 square meters. And you can also find its weighted area using pi d2 L2, okay? And of course, L2 is 72 meters in this case. So you multiply these and you will find that the rubbing surface for the second branch is 248.814 square meters, okay? So we have A1, S1, A2, and S2. And so we can come and plug these numbers in this equation, and that will help us to find an expression of Q1 in terms of Q2. Okay, so that is what I am going to do. So going from this equation, which is the same equation we have there, okay, plugging in now these numbers, okay, that gives me this, okay. And of course, it's A1 cubed, so you put A1 here and then cubed, and it's also A2 cubed on the other side, like that. So you just plug in correctly according to the equations. Do not forget to take it to whatever power you need to take it to. This is another mistake that many people make, and even some of the memos that I have seen where they have questions on this module, they often forget to raise it to whatever power it needs to be raised, okay? And they will carry on providing the solution like that, having forgotten to do maybe cubed or maybe to square something. So be careful with that, okay? And so this is what you should get when you've correctly plugged in the numbers, okay? And from here, you then get that Q1 squared will be equal to 2.187 Q2 squared, okay? And so what you can then do is to take the square root on both sides. So here, square root of Q1 squared will be Q1. And then you need to take the square root of 2.187, and then square root of Q2 squared is just Q2. So when you take the square root on both sides, then you do get an expression of Q1 in terms of Q2. And so if you do that, then you will find that Q1 is equal to 1.479 Q2. Okay, but this is not the end of it. We still are supposed to find the quantities Q1 and Q2. Now, what are we gonna do from this point? We do have this expression of Q1 in terms of Q2. So what you need to do is to remember that initially the sum of the flows that split into the two branches was 25 cubic meters per second. That was the flow rate that was there initially before it split into two. Okay, which means that if you take the quantity that went into the one branch plus the quantity that went into the other branch, what you should get is 25, because that is what was split into the two directions. Okay, and so that's what it means. It means Q1 plus Q2 is equal to 25. And so from here, we can replace this Q1 by this expression, and then we will solve for Q2. So you can just replace Q1 by 1.479 Q2. Okay, so that plus Q2 is equal to 25. And now we have an equation here where only Q2 is the unknown, so we can solve and find Q2. And so you will have 2.479 Q2 is equal to 25, and that will mean that Q2 is equal to 0.085 cubic meters per second. Now that you have Q2, you just need to find Q1. And so because Q1 plus Q2 is equal to 25, therefore Q1 will be equal to 25 minus Q2, which is 25 minus 10,085, and that will give you 14,915 cubic meters per second. And once you've done that, you have established what is the quantity or the flow rate into the first branch and what is the flow rate into the second branch. And that is what they wanted you to do in this question. So that's it for this video. I hope you were able to appreciate how easy this module is. And please, if you did not understand something, just go back and rewatch the video, because it will be really sad to fail on the question on this module. Okay, you shouldn't fail a question that is coming from this module. It's really easy, really straightforward to do. If you need to get in touch with me to request more videos, or maybe to request the notes that I used in this presentation, feel free to contact me using the number in the description. Thank you so much.